The Skeletonics ARRIVE is a full-body non-powered exoskeleton developed by Skeletonics in Japan. It was released in 2021 for entertainment and live demonstrations. The system mirrors the wearer's motion without motors or batteries. It stands 9 feet 2 inches tall, weighs 88 pounds, and operates entirely through mechanical linkages. Skeletonics began experimenting with large human-scale linkages in 2010. In 2017, the prototype codenamed ARRIVE was exhibited at Robotic in Japan. By 2022, the commercial model ARRIVE was introduced with refined link mechanisms, reduced weight, and faster donning time. Current applications focus on entertainment and events, with future expansion toward hybrid systems. The exoskeleton includes a head unit for visual feedback and balance, a torso frame with pivot connections, shoulder linkages that transfer upper arm rotation, elbow joints that mirror flexion and extension, hip joints that translate human knee movement, and foot platforms that maintain ground contact and distribute weight. The ARRIVE is a passive exoskeleton. Human motion drives a 4-bar linkage system that mirrors joint rotation. The exoskeleton's joint angle is proportional to the wearer's joint angle, scaled by the linkage ratio. Torque transfer is determined by the ratio of exoskeleton link length to human limb length. This means the wearer's effort is multiplied or reduced depending on geometry, allowing synchronized and expressive motion without motors. The exoskeleton raises the combined center of mass, which reduces stability. Balance is maintained when the projection of the center of mass stays within the base of support. A wider stance and symmetrical mass increase stability. Controlled shifts of the center of mass maintain balance during movement. The stability margin is defined as the distance between the projected center of mass and the boundary of the base of support. Torque at a joint is calculated as applied force multiplied by lever arm length. Longer exoskeleton limbs increase the lever arm, which increases torque. This amplifies joint forces and energy demand. To reduce user fatigue, lightweight linkages are used to distribute loads efficiently. The frame uses lightweight materials such as aluminum alloys and composite polymers, chosen for their high stiffness-to-weight ratio. A hollow tube structure increases the moment of inertia while minimizing mass. Stress at a joint is determined by bending moment multiplied by distance from the neutral axis, divided by the moment of inertia. Increasing the moment of inertia reduces stress for the same applied load. Load-bearing joints experience bending stress and cyclic loading. Alternating stress is calculated as the difference between maximum and minimum stress divided by 2. Reducing cyclic stress extends fatigue life. Rounded joints and reinforced linkages distribute stress more uniformly, reducing the risk of fatigue failure. Finite element analysis was performed using aluminum alloy AA6061. A torque of 50 Nm was applied at the shoulder linkage, with fixed support at the foot base and gravitational loading of 9.81 meters per second squared. Results showed maximum stress of 42 megapascals, displacement of 3.5 millimeters, and a safety factor of 2.5. These results confirm structural integrity under user-generated torque. The Skeletonics ARRIVE mirrors human movement through mechanical synchronization. Motion is driven by the wearer's body via linkages and pivot joints. Proper joint alignment ensures smooth, symmetrical motion. When alignment is correct, the phase difference between human and exoskeleton motion approaches zero, maintaining force feedback and coordination. The exoskeleton includes adjustable joints and straps to fit different body sizes. Padding reduces localized pressure and shear forces. Balanced mass distribution lowers strain and fatigue. Proper biomechanical alignment minimizes muscle compensation and joint stress. Stress analysis shows that bending stress is influenced by the applied moment divided by the section properties, and axial force divided by cross-sectional area. Maintenance involves 4 steps. First, inspect joints, fasteners, and cables. Second, detach sections by loosening fasteners and removing frame parts. Third, reattach by tightening M5 fasteners to 6 Nm using 4 and 5 mm tools. Fourth, verify the function by testing joint motion and alignment. Safety precautions include disconnecting power and wearing protective equipment. The Skeletonics ARRIVE requires the user to generate all movement energy, which can cause fatigue. Misalignment may create shear forces or unnatural torque transfer. The elevated center of mass increases tipping risk during rapid motion. Continuous loading can loosen joints or cause material fatigue. Passive linkages limit precision for fine motor tasks. Environmental conditions such as temperature, humidity, and surface type affect performance. Demonstrations are limited in duration and require operator supervision.